for all x modulus value of x minus a less than delta and modulus value of y minus b less than delta. Now, we want to prove that f plus g is also continuous. Then start from modulus value of f plus g x y minus f plus g a b. We want to prove that this is less than epsilon. Now, opening the bracket, we got f of x y plus g of x y minus f of a b minus g of a b, and now we are taking together f of x y minus f of a b and plus g of x y minus g a b. Now, applying the inequality that modulus of a plus b is less than equal to modulus of a plus modulus of b. So, this is less than equal to modulus of f of x y minus f of a b plus modulus of g of x y minus g of a b. And now, substituting from 4th and 5th the values of these two differences, we got f of x y minus f of a b less than epsilon by 2 and g of x y minus g of a b less than epsilon by 2. So, the whole function is equal to epsilon. Hence, modulus value of f plus g x y minus f plus g a b less than epsilon for all modulus of x minus a less than delta and y minus b less than delta. Then by definition of continuity, we got f plus g is continuous on a b. Now, after theoretical part, by completing the definitions and theorems, we are going to use these definitions to take the numerical problems. So, here it is given that A is a set of elements of x y such that x lies between 0 and 1 and y lies between 0 and 1, and x y belongs to R. Here function is from a to r defined by f of x y is equal to x plus y. We want to show that limit of f of x y as x y tends to 0 and half is equal to half. Now, we know if what is the definition of limit? We know a function f x y is said to tend to number L as x y tends to a b if corresponding to any pre-assigned positive number epsilon, however small, we can find a positive number delta depending upon epsilon such that modulus of f of x y minus L less than epsilon for all x y for which modulus of x y minus a b lies between 0 and b. Now, here we will compare all the components, all the like here x y is equal to 0 and half, that is a b is equal to 0 and half, and a b is equal to 0 and half and L is equal to half. So, therefore, modulus value of x minus 0 less than delta and y minus half less than delta. We want to prove that modulus of f of x y minus half less than epsilon by 2 epsilon. Now, considering the modulus of f of x y minus half, substituting the value of f of x y, we got x plus y minus half. So, this is equal to x plus modulus value of x plus y minus half, which is less than equal to modulus of x plus modulus of y minus half. Now, from second, we know this is less than delta plus delta, which is equal to 2 into epsilon by 2, which is equal to epsilon, because delta is here equal to epsilon by 2. That is, we are choosing delta is equal to epsilon by. We have to choose the value of delta depending upon epsilon only. So, what we got? Modulus of f of x y minus half less than epsilon for all x minus 0 less than delta and modulus of y minus half less than delta. Then by definition of limit of a function of two variables, we got limit of f of x y as x y tends to 0 and half is equal to half, and hence the result. Let us take up the second problem. This is also a very important problem when a function is from r square to r defined by, why we are taking r square? Because here two independent variables we are considering x and y. So, and it is going to one function, that is z, which is equal to, which is in R only. So, here R square to R is defined by f of x y is equal to x sine 1 over y plus y sine 1 over x not equal to 0, y not equal to 0. Then we want to prove that limit of f of x y as x y tends to 0 0 is equal to 0. Here we are given that epsilon greater than 0 and we are selecting delta is equal to epsilon by 2 such that modulus of x minus 0 lies between 0 and delta and modulus of y minus 0 less than delta, because here a and b are both 0. So, modulus of x minus a lies between 0 and delta and modulus of y minus b less than delta. Now, consider modulus of f of x y minus L, here L is also 0. So, modulus of f of x y minus 0. Substituting the value of f of x y from first, what we got, x sine 1 over y plus y sine 1 over x minus 0, which is less than equal to modulus of x sine 1 over y plus y sine 1 over x, because modulus of a plus b is always less than equal to again a modulus of a plus modulus of v. Now, this is equal to modulus of x and modulus of sine of 1 over y and plus modulus of y modulus of sine 1 over x. We know the value of sine theta is always less than equal to y and modulus of modulus of sine 1 over x is less than equal to 1 and modulus of sine 1 over y is less than equal to 1. So, this function is all less than equal to 1 modulus of x plus modulus of y. This can be written as modulus of x minus 0 plus modulus of y minus 0, which is already given by using second and third. We get this is equal to delta plus delta, because modulus of x minus 0 less than delta, modulus of y minus 0 less than delta, which is equal to 2 delta, which is equal to 2 into epsilon by 2, because we have already assumed that delta is equal to epsilon by 2, which is equal to epsilon. So, what we got, modulus of f of x y minus 0 less than epsilon for modulus of x minus 0 less than delta and y minus 0 less than delta. So, that implies limit of f of x y as x y tends to 0 0 is equal to 0. This is given by the definition of limit of function of two variables. Taking up the third problem, now we will take the level function. Level function is a function when we put this function equal to a constant value. Here we will find the path where the function is either it is defined or not defined. Here function is from r square to r defined by f of x y is equal to x minus 2y over x plus 2y, where x is not equal to 0 and y is not equal to 0. Then we want to show that limit of f of x y as x y tends to 0 0 does not exist. We are taking x y tends to 0 0 along the path y is equal to mx, because we are given in the function y, if we are dividing the function by x throughout, then we will get the right hand side of the given function f of y over x. So, we are considering y over x equal to m, which is known as level function. So, we will prove such questions by taking the function equal to constant value. Therefore, limit of f of x y as x y tends to 0 0 is equal to limit of x y tends to 0 0 of x minus 2y over x plus 2y, because here given f of x y is equal to x minus 2y over x plus 2y. Now, we assume that y is equal to mx, then substituting the y is equal to mx in this function, we got limit of x minus 2 mx over x plus mx as x y tends to 0 0. Now, here on the numerator and denominator x is common and cancelled, then this is equal to limit of 1 minus 2 m over 1 plus m as x y tends to 0 0. there is no x and there is no y's, and this is equal to constant value 1 minus 2m over 1 plus m. So, that means our limit of f of x y as x y tends to 0 0 will take different values for different values of m. So, limit of f of x y is not unique when x y tends to 0 0. So, that implies limit of f of x y does not exist. Now, next problem is show that the function f of x y is equal to 2x square y over x 4 plus y square has no limit as x y approaches 0 0. Now, we are taking the function the curve y is equal to k x square, where x is not equal to 0. The function has constant value. Here f of x y as y is equal to k x square is equal to 2x square over x 4 plus y square when y is equal to k x square, which is equal to 2x square into k x square over x 4 plus k x square raised to power 2, for which is equal to 2 k x 4 over x 4 plus k square x 4. Now, in the denominator and numerator x 4 is common, which can be taken common and cancelled, which is equal to 2 k over 1 plus k square. Therefore, limit of f of x y as x y tends to 0 0 along the path y is equal to k x square is equal to limit of f of x y as y is equal to k x square x y tends to 0 0, which is we have already found out that this is equal to 2 k over 1 plus k square. So, the limit varies with the path of approach. Suppose x y approaches 0 along the parabola y is equal to x square. So, here we are taken k is equal to 1, then we got limit is equal to 1. Again, when we taking x y approaches 0 0 along the path x axis, that is k is equal to 0 and the limit is 0. Then by the two path test, f has no limit as x y approaches 0 0. So, we got two limits for different paths. So, limit is not unique, it means limit does not exist. Again, taking the fifth problem, if a function f be defined by f of x y is equal to x square minus y square over x square plus y square as x y not equal to 0 0, then show that two iterated limits, limit of f of x y as y tends to 0 over limit of x tends to 0 and limit of f of x y as x tends to 0 over limit y tends to 0 exist, but the simultaneous limit f of x y when both x and y tends to 0 0 does not exist. So, here it is a particular case and it is very important that how the it is an example of, sometimes in the paper it is asked, then give an example of a function where the limits exist, but the simultaneous limit does not exist. Repeated limits are here existing, but not the simultaneous exist. How come? First of all, consider the limit of f of x y as y tends to 0. Then substituting the value of f of x y, we got limit of x square minus y square over x square plus y square as y tends to 0, which will be x y will be 0, then the inside function will be x square over x square minus 0 over x square plus 0. So, this is equal to limit of x square over x square as x tends to 0, and this is equal to limit of 1 as x tends to 0, which is equal to always 1. Again, taking other way around, limit of f of x y as x tends to 0 is equal to limit of x square minus y square over x square plus y square as x tends to 0. Substituting the value of 0 0, we got 0, inside we got 0 minus y square over 0 plus y square. This is equal to minus y square over y square. So, this is equal to limit of minus y square over y square as y tends to 0. Now, inside is equal to limit of y tends to 0 of minus 1, which is always equal to minus 1. So, iterated limit, two iterated limits, limit of f of x y as y tends to 0 and over as limit x tends to 0, and limit of f of x y as x tends to 0 and as y tends to 0, both exist and equal to 1 and minus 1 independently. But now we are taking the simultaneous limit, whether it exists or not. Now, we will take the limit along the path y over x is equal to m. So, we are considering the level function y over x is equal to m. Now, here limit of f of x y as x y tends to 0 0 is equal to limit of x square minus y square over x square plus y square over as x y tends to 0 0. So, which is equal to limit of x square minus m square x square over x square plus m square x square as x tends to 0. We are substituting the value of y is equal to x, and so there is only one limit of as x tends to 0. So, again in the numerator and denominator x square is common. So, we got limit of 1 minus m square over 1 plus m square as x tends to 0, which is a constant value. So, there is no meaning of limit. So, which is equal to 1 minus m square over 1 plus m square. So, we got simultaneous limit as a function of constant value, which will be different for different values of m. So, this is not unique. So, when the limit is not unique, then it does not exist. So, although iterated limits are existing, but the simultaneous limit of x square minus y square over x square plus y square as x y tends to 0 0 does not exist. Now, next take up another problem of continuity that show that the function f from r square to r defined by f of x y is equal to x y such that x square minus y square over x square plus y square if x y not equal to 0 0 and if it is equal to 0 if x y equal to 0 0 is continuous function. Now, here the value of the function at 0 0 is 0 given. So, we want to prove that f of x y minus f of 0 0 less than epsilon for x minus 0 less than delta, y minus 0 less than delta. Given epsilon greater than 0, we are selecting delta is equal to under root epsilon. This why we are considering delta is equal to under root epsilon. This is always chosen according to our need. You will find out that in the end, to prove the result, we need delta is equal to under root epsilon. Delta is always depending upon epsilon only, such that for modulus of x minus 0 less than delta and modulus of y minus 0 less than delta, consider the function modulus of f of x y minus f of 0 0. Now, f of x y is given function x y into x square minus y square over x square plus y square minus 0, which is equal to modulus of x y and modulus of x square minus y square over x